So let's take a look at why we went through that last video. I'm going to graph this. I want to find the area that's bounded by all of these curves. So y equals x plus 5 is a straight line that goes through 5 and negative 5. And then I've got y equals 2, which is approximately here. And y equals negative 1. Let me extend that there. And y squared equals x, which is a sideways parabola. It's not actually a function, it's a sideways parabola. So there we go. Y squared equals x. So what area is enclosed by all of these four colored lines? Well, hopefully you'll see that it's this area right here. And if we were to consider vertical rectangles, notice that what's on top, the function on top, is changing. In the first section, it's the purple line that's on the top and the green one that's on the bottom. So in area 1, we've got the purple line on top, the green one on the bottom. In area 2, I've got the red line on top and the green one on bottom. And in area 3, I've got the red one on top and the orange one on the bottom. And on area 4, which is this little one down here, I've got the orange one on the top and the green one on the bottom. So we'd have to do this 4 separate times, adding all the areas, and it would be not impossible, but messy. So let's think about this instead as going from left to right. So adding the rectangles this way. And really what we're monitoring is what is the x value on the left and what's on the right. And consistently through the entire area, this value is on the left and the orange is on the right. So this is the left function and this is the right function. So notice that we don't have to do a whole bunch of switching. We've always got the same function on the left and the one on the right. That means that doing horizontally laid rectangles would be an easier way to look at it than doing vertical rectangles. And that means I'm going to integrate using my y variable. So, so I'm going to integrate, and I'm going to take all of the one on the right is the bigger one, so x to the right minus x to the left, that's the length of each rectangle. And I'm going to multiply it by the width of the rectangle, which is dy, and I'm going to integrate it from the least y value to the biggest y value, which is from -1 to 2. So now I've got to replace, notice I've got a kind of a mixture here of variables, and I need to only have one, and I need the y's, so that I need to replace all of these with y's. But that's easy to do. The left one is, the right one here is the parabola. So the parabola in terms of y is y squared minus the left bound, which is the straight line, and in terms of y, I have x equals y minus 5. So the yellow might not be a good color, they're white. X minus, or not x minus 5, y minus 5. So here's the right bound, there's the left bound, and we're integrating with respect to y. So I'm going to multiply this negative in, and I'm going from -1 to 2 on the y-axis. So integrating, I've kind of lost haven't got enough room here, so I'm going to I think I'm going to do this on a new page because it'll just get too messy. So we're going from -1 to 2 of y squared minus, what was it? Y squared minus y plus 5 dy. So each of these variables, the exponent goes up by 1, and you divide by that number, so that's y goes up to 2 plus 5y, and we're integrating from -1 to 2. So So plugging in my y values, plugging in the 2 first, so it's 2 cubed over 3 minus 2 squared over 2 plus 5 times 2, and I'm going to subtract when I've plugged in the -1. So -1 cubed minus -1 squared over 2 plus 5 times 1. And doing all that, I can then evaluate, and I get 16.5. I know I'm doing that really quickly, but you can press pause and give it make sure that I'm right. So we've got 16.5 units squared. So what that means is that this area here is 16.5 units squared. So in this case, it was easier to think of going from left to right instead of from up to down. And the best way to identify which, if that's the case, is that if you're switching, if you've got to divide it up in too many areas, going the traditional